Where is the speaker? So that okay. So welcome everyone to this sort of third part of this course. If you don't remember me, I don't blame you because I was here for only the very first lecture. So the welcome lecture. So my name is Kvellestad, and I'm a postdoc over there, just in the other part of this floor, over at the theoretical particle physics. So what I do in my day-to-day work is I write codes for doing statistical analysis of new theories in particle physics. That's my background. That's what I'm supposed to do. And as a consequence, I've gotten interested in Bayesian statistics, and I've gotten interested in Gaussian processes, and hence why I'm giving this set of lectures, and also to give poor Morten some time off, because he's done a heroic effort so far. The idea is that I will give a series of 3 to 4, I will lecture 3 to 4 Mondays, I think, now, depending on how much we need. But our starting point is that we have sort of a practical issue that we should decide together, I think. So we have the lecture today, but then next Monday is the Easter week, which is not officially, it's not a public holiday, the Monday, but traditionally no one lectures on that Monday to Wednesday. And then the following Monday, which is then Monday, so next Monday is April 11th, and then it's April 18th, and that is a public holiday. So we're not going to have a lecture on that Monday. But I think it'll be bad if we now have one lecture and then it's 3 weeks until the next one. So the question is essentially, what do you guys prefer? The way I see it is, I think we have 3 options. Either we actually meet for a lecture next Monday, or we try to meet for a lecture on Tuesday the 19th. Or the third option is that I simply record a lecture and you watch it whenever. So there seems to be some enthusiasm for alternative 2, at least, that we meet on Tuesday 19th. No? No. That's a no from you?
I won't be here and I won't be able to listen to anything, but I can listen to the recording.
But you can listen to the recording, right? So for you, it doesn't really matter then if I just record a lecture or the rest of us. Or
Monday would be the best option, but I can listen to the recording.
So personally, I prefer not to do it this next Monday, because if we decide to do it next Monday, then I'm definitely not traveling anywhere. If we decide to not do it next Monday, I might be traveling somewhere. But okay, any other strong opinions? Are people okay with us trying to find some time on Tuesday the 19th? Okay, thanks. That's settled. So let's write a little bit about the plan for these lectures. So my plan is that it will be essentially 3 parts to this. And the first will be today, which will be one of my favorite topics, which is interpretations of probability, because we need to understand what we do understand and what we don't understand about probabilities before start discussing Bayesian statistics. And as part of that, I will try to do a sort of a very quick refresher on probability theory. This will be very basic, but again, it's the sort of concepts that we need to be precise on and clear on before going into Gaussian processes, especially because Gaussian processes I have sort of I love the concept, the framework. I find it very intuitive and very natural to work with. But the notation is, if you read Gaussian Processes papers, the notation is terrible. I mean, there are so many papers that I read where it's sort of, I understand qualitatively what they're doing, but trying to understand notation takes a lot of work. So that's why we should at least be clear on our notation for various probabilities. So this is sort of philosophy plus the pure philosophy plus math part. The second part I want to do, or the plan is to do some what I just call aspects of Bayesian statistics. And this will be sort of both the general framework, philosophy, way of thinking about it, in particular way of thinking about parameter estimation and model comparison, which are sort of the two main, or way to divide up the two main applications. And I hope that at least one of the techniques that I want to introduce here is something called nested sampling. And many of you heard about this or used it. That's good. We're learning something new. That's very good. I'm betting many of you have heard and or used Markov chain Monte Carlo, right? So, I mean, in Bayesian statistics, one of the reasons why it went from sort of being a special interest of people with an interest in the philosophical foundations of statistics and probability to something that's really applicable is that we suddenly got especially during the 90s, we got the algorithms and the computational power to actually perform large-scale Markov chain Monte Carlos, which is a method for sampling from probability distributions. And in Bayesian statistics, everything is a probability distribution, and you essentially end up computing a lot of high-dimensional integrals. So then having Markov chain Monte Carlo methods is a useful, or is essentially what made this possible. Right? But nested sampling is an alternative framework for essentially also for sampling from probability distributions. And it's a really, really powerful method. And since less people have heard about it and used it, I think it's worth introducing that. So this will essentially be pure stats or statistics. And then the final part is the Gaussian processes. And this is what you would typically then call machine learning part of this. To be honest, the distinctions get a bit blurry. From the Bayesian point of view, it's like it's probabilities, probabilities, and probabilities. These three parts. But of course there are clear differences there. The main references that I would advise you to look at if you want some more background information is for the stats part. It's a book by Sylvia, and it's called Data Analysis Bayesian Tutorial. For the machine learning or GP, Gaussian processes part, it's the GP Bible. It's not called that, but it's the standard reference for it. It's typically like reference 1 or reference 2 for anyone doing any paper or text on GPs. So this is Rasmussen and Williams, and it's called Processes for, okay, I'm just going to write ML for machine learning. And the good thing about this book is that it's available free online as a PDF. if you just Google Gaussian Processes book Rasmussen, you get it. And I mean, it's the authors themselves that put it online, so it's not something shady. So these are my main actual references, and then I want to point you to a real gem in the scientific literature. And well, I won't be using this as much, but you might have heard of this, I'm not sure. E.T. Jaynes, famous physicist who got famously interested in Bayesian statistics and Bayesian probability. So he turned his focus to that. And he wrote a huge book. He didn't finish it before he died, but a friend or a colleague finished it for him. And it's called Probability Theory, the Logic of Science. And this is a brilliant book, but it's about 1,000 pages. I definitely haven't read all it, but it's a brilliant and it's a super provocative book, and that makes it fun to read. This guy is so opinionated, and you realize from page 1, but he also has essentially the arguments he needs to be opinionated. So he is a hardcore Bayesian. And if you read this and don't come away at least partially convinced by this, you have a stronger defense mechanism than I do, at least. This was one of the texts that made me a Bayesian. So anyway, it's anyway a really, really interesting read. So but we need to understand, so let's start with probability. So we need to understand what this is. And I'm going to start by doing an experiment. So I have a die. I claim it's a regular 6-sided die. And if I throw it, what's the probability that I get a 6? Any opinions? 1/6. Okay, yeah, that's a natural choice. I would probably choose the same. Okay, so you claim it's a probability of 1/6. Now I throw it. What's the probability now? Sorry?
0.5.
Why is it 0.5?
Because it's either yes or no.
Sure, but there are many things in life that have 2 possible outcomes, but I still wouldn't claim that it's 50-50. For instance, if I asked you, this die throw has 2 possible outcomes, either I get a 6 or I don't get a 6. I would naturally then claim that, at least before I threw it, I would say the probability of getting a 6 was 1/6. The probability of not getting a 6 was 5/6. So not 50-50, right? And just another example, either aliens have visited the Earth or they haven't. Would you claim it's a 50-50 probability that they have? I don't think you would, right? But it's a good point, because a lot of it's a very and sometimes it's arguably the most rational choice to say, because there are 2 options, I'm going to say it's 50-50. So, but anyway, okay, so perhaps not 50-50, but what's your probability that this is a 6? I mean, I have my probability, but I'm not telling you.
It's the same as before?
The same as before? Very good. I would probably say the same if I were in your shoes. Of course, I'm not. So, and so currently, I would say that I have a different probability than you. If you claim it's 1/6, then I disagree. And this is interesting, right? It happened to be a 4, right? In this case. But this is interesting because what does this tell us about probability, or at least how we want to use probability? Does it make sense for us to disagree on probability?
Depends on the prior knowledge.
Depends on the prior knowledge, right? Or yeah, or so prior. Yeah, I agree. Prior knowledge. Though prior ends up, the word prior ends up taking sort of a special meaning in Bayesian statistics. So I would just say something like it depends on what information you have, right? So, for instance, we could say what's the probability of a 6 given some set of information, I1. Apparently, that's not equal to, or doesn't have to be equal to probability that it was a 6 given some other information, I2. But then it's clear that we're using probability to be related to information in some sense. But how would you define probability? If I have some variable x, random variable or uncertain variable, what does P of x mean? Or how is probability, this mathematical object, how is it defined? Any suggestions? I mean, you're guaranteed seen one definition, at least, which is probably the one you learn in high school if you did probability in high school.
It's when we sample a lot of times.
Exactly, right? It's so arguably the most, I'm not sure I want to say common, but the definition you're thinking of is probably this one. So I define P of x to be a limit if I perform an infinite number of trials, and I take the ratio, the number of times that x happens, divided by the total number of trials. Right. So this seems fine, but just 5 minutes ago, we realized that you had a different probability from me. And where is you and me in this definition? Right? Can we even use this definition to talk about the probability of a single event or something that has happened?
You couldn't use that sample to kind of estimate the probability for any other theorem place, because it wouldn't really help destroying the ones.
Right, but if I did but if this throw was just 1 out of 1 million throws, then presumably I could have used it to estimate probability for, or I think, yeah, most people would say yes, and I think I would agree, at least if I was working under this definition of probability. But this definition really defines what we mean with probability. It defines it as an infinite limit, right? We can never perform an infinite number of repetitions of anything. And I mean, regardless of how many trials we do, it will always be sort of an infinitely small fraction of an infinite repetition, right? So you're always sort of infinitely far away from this, but I mean, we can still use it. I mean, if I did 100 throws of this die, I could end up with something like saying that the probability of getting a 6 is was 1/6. It's like 1.825. Is it? No. Okay.
0.166.
Yeah. Thanks. 0.1. Okay, so say I did 100 throws and I got this to be this. I don't know. Or rather, I just got this, right? After 100. rows, but this was after 100 rows. This can't actually be the infinite probability, so it's just an estimate. So I'm gonna assign some uncertainty to it. Okay, let's say I estimated this uncertainty plus minus 2%. But what does that uncertainty then mean? So I ended up with an uncertainty here because I wasn't able to repeat an experiment an infinite number of times. So I ended up with an uncertainty, but that uncertainty is itself a probability, right? So that uncertainty then refers to what if I was to perform an infinite number of 100 repetition experiments, right? How much variation do I then expect? So that's an uncertainty. It's a probability that expresses an uncertainty on a probability, but at least from the way I see it, I end up biting my own tail here. That, okay, I had a problem that I couldn't perform an infinite number of trials. So I end up with an estimate, but that estimate itself refers back to an infinite number of trials, etc. This is a bit philosophical, and I mean, you all know that this actually works pretty well in practice for repeatable stuff. But the philosophical point is important, and the take-home message is that if I say that P of X is 10%, we don't know what this means. Or at least we don't agree on what it means. We know how to do math with it. We know how to use it to some extent, but we don't agree on what it means. And to illustrate this, probably you all know about the Stanford Encyclopedia of Philosophy, and if you don't, you definitely should know about it. It's an online, open, free Encyclopedia of Philosophy, and it's very, very good, and all scientists should spend a little bit more time reading these pages than they probably do. And here you find, okay, there's an own article for the interpretations of probability. And I'm quite a fan of this Bertrand Russell quote here. Probability is the most important concept in modern science, especially as nobody has the slightest notion of what it means, which is quite nice. But if you read this, the take-home message here is that you see there's what they call the main interpretations. There's like a handful, 5 to 6 main interpretations of probability. So different views on what P of X actually means. What we will do is that we will discuss 2 main interpretations. And essentially, I'm using this to introduce Bayesian statistics, to contrast this to this understanding of probability, which is a frequentist one. So I'm going to claim that, at least in practice, in scientific applications, we have 2 main interpretations. It's the frequentist, and here P of X is defined. Again, I'm just going to rewrite that same definition: an infinite limit of the number of trials where you get X divided by the total number of trials. The alternative, the other interpretation, which will be our starting point for these lectures, is the Bayesian definition of probability. And there are as many views on this as there are Bayesian statisticians, but I think almost everyone would agree on this, the following definition. By the P of X, we mean our degree of belief or degree of knowledge that X is true. And the reason why I had to put belief/knowledge is that there are two main schools within the Bayesian camp. It's the subjective Bayesians and the objective Bayesians. So if you're a subjective Bayesian, then you typically say degree of belief. If you're an objective Bayesian, say degree of knowledge. And one of the things that makes this so powerful is that, I mean, when looking at it like this, it looks like a much vaguer definition of probability than probability is this mathematical infinite limit that looks much more precise. But by being, let's say, a bit more vague, you also expand the use cases where you can actually apply probability. Because in the frequentist case, you are restricted to only using probability when things are repeatable. And that's why we got into the problem when I had thrown the die and I was asking you about the probability for that, etc. Then that was a single event. We could discuss about, okay, what if this was 1 out of 1,000 events? Then we got into, okay, that seemed more natural. But as soon as I had thrown that die, that was a single event that had happened, and it got very difficult to talk about that probability in a fragmentist sense, in a sort of completely objective sense. So fragmentists can only talk about probability for things that are repeatable, at least in principle repeatable. And the Bayesians, with that definition of probability, you can apply it to anything, any statement. So I can ask about what's the probability that the moon is made of cheese? Or what is the probability that there is life on Mars? What is the probability that my partner loves me? Stuff like that, right? That's because I'm literally just saying, what's my degree of belief? And I'm a subjective Bayesian. So that's why I will keep saying degree of belief. But if you're an objective Bayesian, you might think that, okay, I should have said degree of knowledge. But anyway, we can apply it to any statement. And that, of course, incorporates the sort of statements that you would naturally use frequentist statistics for. I can, of course, as a Bayesian, ask if I perform 1,000 throws with this die, what's my degree of belief about the fraction of times I'll get a 6, right? So in those limits, in the limits where you have a lot of data, you will typically see that these questions sort of merge, and the difference between being a Bayesian and being a frequentist becomes less noticeable. It's still there philosophically, but essentially, if you have enough data, in most cases, there are corner cases, but in almost any case, if you have enough data, then sort of the conclusions you draw are obvious, regardless of what your view on probability is. But in the case where you don't have a lot of data, these differences matter, both on what you think about things and also what methods you apply. So one of the reasons why, so what's important to point out is that both these definitions satisfy the Kolmogorov axioms, right? So if you did probability theory, you've heard of the Kolmogorov axioms, which is one way of defining, is the axioms that defines the mathematical properties of P of X, right? So as long as your P of X satisfies the Kolmogorov axioms, you get all the usual math of probability theory. So frequentists and Bayesians don't disagree on the formulas, they disagree on the interpretation of the formulas. And one of the reasons why many people, or I guess Bayesians in general, find this Bayesian definition of probability to be plausible or let's say, yeah, I guess plausible, is that there was a physicist/statistician called Cox and others. I mean, this interpretation of probability, of course, goes all the way back to the Reverend Thomas Bayes, but it's especially in, I think it was in the 40s. This guy called Cox and others were looking into, okay, you have formal logic, Boolean logic, right, which is essentially rules for how to reason consistently if your statements are either true or false, right? How to be consistent about your reasoning if all your statements are either true or false, that's Boolean logic. How do you reason if your statements are not 100% true or false? How can you consistently reason under uncertainty? And what Cox and others then were looking at was, okay, they were setting up some desired requirements for, okay, what sort of requirements should such a framework, mathematical framework, satisfy? And it was also sort of like common sense requirements that, okay, for instance, you should be able to rank various statements, order them according to how certain you are. And as soon as you said that I should be able to rank sort of trustworthiness of statements, then you can just relate them to the real numbers, and then you have a system for ranking, for ordering stuff, and various other requirements like that, and they tried to derive a mathematical framework for reasoning under uncertainty. And what they derived was just the old rules of probability theory. So they rediscovered probability theory, not starting from the Kolmogorov axioms, but starting from what should a system for reasoning under uncertainty satisfy. And the fact that that gives you the rules of probability theory, to a lot of us, that sort of tells us that actually probability theory is much more general than being connected only to repeatable stuff. So that's one of the reasons why I and others find this quite convincing. Where this really matters, I mean, interrupts at any time, by the way. One of the places where this really matters is in what sort of questions you're allowed to ask within the different frameworks. So if you're a frequentist, then okay, I'll ask you instead. Might be a leading question. So this is, can I ask a frequentist, what is the probability of this hypothesis being true given some set of data? Would a frequentist be happy to assign a number to this? Any?
On the data, like the
Sorry?
size of the data, if it's large enough.
So you're saying if it's large enough, then perhaps a frequentist would be willing to assign a, yeah. I disagree. It's a good suggestion though, because you're sort of saying that at least a frequentist would need a lot of data. But the probability of a hypothesis doesn't make sense for a frequentist, because you can't take the infinite limit of a hypothesis. A hypothesis is not something repeatable. Data might come from some repeatable experiments. So a frequentist will not use that sort of probabilities. They will, of course, be perfectly happy to use this type of probability, which is saying if I assume some hypothesis, for instance, I can assume that this that the probability for getting a 6 in the die throw is 1/6. If I make that assumption, I assume that hypothesis is true, then I can compute the probabilities for any sort of data I might get from this type of repeatable experiments. So frequentists don't ask the first question, they're happy to ask the second.
Can I ask a question?
Yeah, absolutely. Go ahead.
So I guess maybe I have a bad understanding of frequentist definition, but isn't it also correct to say that frequentists believe that the probability of X would be how often X occurs in nature, independent of a hypothesis? So and I guess there's no limit that you take in that case because it's not dependent on the experiments that you do. It's just the frequency of things that happen objectively.
Yeah, exactly. I see your point, and it's actually something we'll come on to, whether nature might sort of save, quote unquote, the frequentist definition. But say I asked the frequentists what's the probability of life on Mars, right? They would struggle with that exact question. But if I instead asked what's the probability of life forming on Mars-like planets, okay, they might be more happy with that because we at least we can imagine that there being more samples of planets that look like Mars. But then again, you'll end up with that probability being completely dependent on how wide is your definition of Mars-like. If you said it had to be exactly Mars, then either there is life on Mars or there isn't life on Mars. And the frequentists would say, okay, if you want to assign a probability to it, it's either 0% or 100%. Whereas Evasion would be happy with saying it's 0.1%.
But wouldn't the probability be, so if you look at the history of the universe and after that, you just count the number of lives that have occurred on Mars? Of course, you can't actually do it, but like the definition would tell you that it's, let's say in the future we go live on Mars, so it would be 1 over, I'm not sure how we would do it, but
yeah, exactly. So if the question is there life on Mars or not, as soon as you find some life on Mars, then you've answered that question, yes. So then it's okay, yeah. The probability is 100%, or it's not. What a frequentist, and this is, but the question you raise is super interesting because it sort of illustrates how a frequentist might go about answering something like that. And essentially, what the frequentist would have to do is to start from some sort of probability assumptions about the different ways in which the universe can evolve. And then you can imagine the frequentist running a universe simulation 1,000 times or 1,000,000 times. And in each universe sort of identify Mars and check did life evolve or not. So the frequentist, in order to try to answer these sort of questions, the frequentist will often take the one data point we have, make assumptions about what sort of probability distributions this one sample was generated from, and then sample a gazillion more data like that. Bayesian would be more conservative about that, saying, I don't want to draw. So at least a lot of Bayesians feel quite strongly about something called the likelihood principle, which is essentially saying your inference should only be based on the data you have, not also hypothetical data that you assume you would get if you were to repeat experiments. Did that sort of answer your question?
Yeah, I think so.
Cool. So Bayesians can use both probabilities. And here we need to then get into the difference between the subjective and the objective Bayesians. So subjective and objective Bayesians are all happy with say that I have some probability, P me, for X, given some background information I1. And this does not have to equal your probability for X if you have some different background information. So this is essentially the die throw example, right? Where my probability and your probability differed because we had different, we were conditioning on different sets of information.
What would you have said?
I would have said 0 because I knew it was a 4.
Yeah.
Right? So my probability that it was a 6 would either be 0 or sort of at the level of just accounting for the fact that I might be hallucinating, right? At that level. An interesting question would be, I didn't do it, but I could have thrown the die. I looked at it and said it was a 4, or knew it was a 4, and I told you it's a 4.
Yeah.
What's your probability that it's a 6? Because then you need to factor in, well, he told me the result, but do I trust this guy? Right? And you don't, so even in that case where you might think that we have the same background information, we actually don't, because I have the direct experience, you have only information through me, which might be unreliable, right? But
Bayesian would also assume that there is some underlying true probability.
This is exactly what we're getting at. Very good. So subjective and objective Bayesians are perfectly happy with these two probabilities being unequal. But objective Bayesians, they require that if we have the same background information, then so if both of us have background information I1, then we should assign the same probability. That's the objective part of objective Bayesian, is that if for the same set of background information, there is in effect a best way or a true way of assigning probabilities. Subjective Bayesians like me say, nah, it's not. Even if we have the exact same information, I'm philosophically happy with my probability differing from yours. That's what makes me a subjective Bayesian. It might feel unnatural for a scientist. I started out by being a frequentist because I was told by my old physics professor that Bayesian statistics was the devil. And then I got into Bayesian statistics, and my PhD was effectively an objective Bayesian PhD. And now for the past 4 or 5 years, I'm a subjective Bayesian. And the reason is this. And this is essentially the disagreement. When you, take the rules of probability theory. Do the rules of probability theory tell you how to assign, say, the probability of getting heads in a coin flip? Or getting 6 in a die throw? Do you know all the rules, standard rules of probability theory, Bayes' theorem, and rule for total probability, all these just mathematical relations that you derive from the Kolmogorov axioms, for instance. Do they tell you how to assign, say, your starting probability? They don't, right? I like to compare it to differential equations. Differential equations don't tell you how to assign the initial state. A differential equation which means the laws of physics and laws of nature typically, they are relations that relate a starting assumption to a final assumption. If you believe nature is like this now, you should believe that nature is like this a little bit later or in some different place. That's the differential equation. Rules of probability theory, just the bare bone rules, they work the same way. You have to start by assigning some probability. For instance, what's the probability of getting heads? I have to choose a number, but once I've chosen a number for that, the rules of probability theory tells me how to consistently relate that assumption to statements about other experiments. For instance, if I said the probability of getting heads is 50%, then I can use the rules of probability theory to ask what's the what's the probability of getting 50 heads in 150 throws, right? And it'll be a small probability. But that's still, probability theory just gave me a relation between probabilities. And so that means probability theory in itself does not tell us how to assign this probability P of X given I. So being a subjective Bayesian is being completely minimalist and saying, I don't think there are any rules in probability theory beyond these basic rules. If you're an objective Bayesian, you're faced with this practical question that I need to come up with some additional rules. I need to extend probability theory in such a way that I have a rule for how to assign that probability so that we can actually agree. And that's the difference. And there are suggestions for such rules. And I'll just quickly give one example before we stop. So probably the most famous suggestion for such a rule is what's called maximum entropy. And it's actually related to one of the persons developing this was this E.T. James, who wrote this probability theory book. And here, entropy is used in the sense of information theory, in the sense of Shannon entropy. And what it essentially says is that the way to assign a probability is to be as uncertain as you can, but still be consistent with all the information you got. And so for instance, if I have some uncertain variable X, and what we mean by being the most uncertain is, okay, if this is my probability distribution, then that's a more uncertain probability distribution than this, right? If P of X means my degree of belief in something, then here I'm very certain about what's the correct value of X is, here I'm uncertain. And for instance, if I told you, I didn't give you a probability distribution, because for a Bayesian, the probability distribution is everything you need. It contains the complete set of information about the complete specification of your degree of belief in a variable. But what if your colleague performed an experiment and he didn't give you a probability distribution as a result? He only said, I did an experiment, many measurements perhaps, and I found this result. So he only gave you, or she only gave you, those two numbers. Then what should your degree of belief be? You have to assign a probability distribution, being a Bayesian, but how should you choose? If this was, say, your information, then what is your objective probability distribution given this information? And then in that case, this maximum entropy approach essentially tells you what you now know is a central value and a variance or a standard deviation. Any probability distribution has sort of a mean and a standard deviation, but among all the possible probability distributions out there, you should choose the probability distribution that has 0.7 as mean and 0.1 as standard deviation, but that has the largest entropy, maximum entropy, which is the most uncertain one. And this is actually a super interesting result, because the result, if you do that, is that you end up with the normal distribution, the Gaussian. So usually you hear that, well, the normal distribution appears everywhere in science, and it does because of the central limit theorem, right? Which says, okay, you have a random variable that is a sum of many random variables, and if that sum is large enough, independently of how those independent different terms are distributed, that sum will tend towards a normal distribution. And this happens all the time in science because so many of our things end up being affected by 100 different small effects, small random effects, right? And then that's why all your measurements end up like normal distributions. But this gives you another reason for why the normal distribution ends up, or why it might be reasonable to assume normal distributions. It's because it's effectively, when you know something like this, it's effectively the most conservative choice. And so objectivations need to invent new rules like that. Subjectivations like me don't. And let's stop here and take 10 minutes, 15 minutes break. So we've okay. Listen to this in the break. We sort of started already on what I wanted to. The last part of this sort of philosophical discussion is to see how does this matter. A couple of places where this matters, and so let's do. Different interpretations consequences. And the first is, of course, that they give rise to, as we've alluded to, different approaches to statistics. So roughly, right? I mean, okay, as Bayesian, I would say that the distinction isn't that clear, but roughly, probability theory tells you, okay, if you assume some probability, how do you relate it to other probabilities? Statistics is more the question that, given some set of data, what conclusions can I draw? So that's more inference, whereas probability theory is deduction. It's essentially just performing logic from a set of assumptions, whereas statistics is, I have this set of data, I'm gonna try to make some sort of inference towards the general case based on the limited data set. But so if we do parameter estimation, for instance, patients can ask what's the probability of some parameter value given some data. Frequentist cannot ask this, and this then matters for, like, a classic summary of a parameter estimation study is to give a confidence interval, right? Or in Bayesian statistics, the equivalent is a credible interval. So, example, let's use 95% because it's usually the threshold used. Bayesian 95% credible interval. Say my parameter is for, just going to use theta as a parameter. Say that interval is 0.1 to 0.3. And by giving this interval, what I'm literally saying is that my degree of belief, knowledge, that the true theta is within 0.1 to 0.3 is 95%. So I made a simple probability statement about what's my degree of belief that the true value is within this range. Well, it's 95%. If I decided to use 99%, I would end up with a wider interval, 68% shorter intervals. But the statement is a probability about, it's a statement, it's effectively one way of summarizing the underlying probability distribution that I have assigned to theta. Right? I could have summarized it in other ways. I could have just given the mean, for instance, but the best summary would always be to just give the entire probability distribution. But contrast this to a frequentist 95% confidence interval for theta, let's say again 0.1, 2.3. And I'm not going to write out the entire definition, but then what this means for a frequentist is if I was to repeat this experiment an infinite number of times, or at least very, very many times, and perform the data analysis in exactly this way and construct an interval in exactly this way, then 95% of those intervals will contain the true value. So instead of using, again, you sort of see this difference between the Bayesian who prefers to make statements just about the data we got versus the frequentist who says, okay, actually, we're gonna have, we can take the data we got, but we're also gonna have to make assumptions about what would happen if I were to repeat this experiment. And by doing that, they avoid assigning a probability to the parameter value, and instead they can work with probabilities for how these intervals will shift. Because you assume, you model the experiment, you say, I have some data, my observed data point, I'm going to model that as being a sample from an underlying probability distribution, a probability distribution for the data, right? And that means that, okay, if I were to repeat the experiment many times, that means just, okay, I were to sample new data sets from these assumed probability distributions. Then for every repetition, I would get a new 95% confidence interval. These would jump around. They are random because they are functions of your data, which is random, and functions of a random variable are itself a random variable. And then the final probability statement is about the fraction of these intervals that would contain the true value that we all believe exists out there in nature. So this is one of the ways in which this different view on probability ends up giving you different views on parameter estimation. The other, I guess, more philosophical consequence is the question of whether probability necessarily is linked to randomness. I mean, is anything truly random? This, of course, is a big question in philosophy, metaphysics, partial determinism, all that stuff. But if you're a frequentist and you say, just by repeating the experiments, I will get different outcomes, there must be a source for this variability. So take a coin flip, for instance. I agree, even though I'm a Bayesian, I definitely agree that if I were to flip a coin 100 times, I would get approximately 50 heads. But is a coin flip random? A frequentist would talk about like the probability of a random variable, right? So they have to link this to randomness, whereas a Bayesian would typically say it's just an uncertain variable. But is a coin flip random? You say no, I agree. I don't think it's random. At least it's not truly random. It's apparently random.
We could just work out the mechanics that's going on.
Exactly. We could work out the mechanics, right? If we knew all the details of a coin flip, the air currents in the room, if we had the computational power of perfectly computing, we knew the exact initial conditions. This is all classical physics, which is completely deterministic, right? So if I knew the initial conditions perfectly and the boundary conditions perfectly, I could compute exactly what the outcome would be. Meaning that if I were to train for 20 years doing coin flips, I could probably train myself to beat a 50-50 probability. I could probably get so good at flipping coins that I could flip a head with a 60% probability or something like that. Which means that I could travel around and making bets with everyone and becoming rich that way. Or I could build a robot, right? And people have built robots that are so precise at flipping coins that they get effectively almost always the same outcome. So in that case, clearly the probability doesn't seem to be 50-50, even though that's our natural choice. And in the case where you eliminate where you have complete control, you get the same outcome every time. There is no randomness anymore.
But like, we don't know the mechanics. But then if we know that, then the reason why each time there is like a different movement going on, that is coming from somewhere, like our brain. So do we go back to brain? Is something random happening in the brain that produces?
So the way I would view this is that the randomness, or this, what I would call the apparent randomness in a coin flip, what it's just reflecting is it's reflecting my inability to perfectly repeat the same experiment. So effectively then for the frequentist probability to actually come out 50-50, that ends up being connected to some boundaries on what do we actually mean by repeating this experiment. Because apparently if I repeat it too accurately, then that probability starts shifting, and in the end there is no probability, there is no randomness anymore there. So from my point of view, the probability, the 50-50 probability in a coin flip, which I would assign a probability of 50% if I were to flip a coin. But from my point of view, that just expresses my degree of belief about what various initial conditions would lead to, and my inability to choose those initial conditions exactly. So effectively, what it reflects is a lack of information. I don't have complete information about the initial and boundary conditions, and that's why I don't have complete information about the outcome. But you see now what I've done is I've moved away from the randomness, and I've associated the probability in the coin flip to just information, which is again a degree of knowledge or a degree of belief, something like that. So from my point of view, this is coin flips. I mean, the frequentist probability of a coin flip is philosophically problematic because they seem to be related to randomness, but randomness seems to disappear. I'm sure frequentists would argue with me. So I mean, you're getting my very much subjective point of view on this.
But in this case, if we repeated the experiment, exactly the same experiment in coins for too many times, then it's the other way around. It's the other way around. The frequentist approach will not end up with the same probability of Bayesian approach, but it will end up with either 0 or 1.
No, but that would Evasion also do. Because even if I thought I initially had a 50-50% for the first flip, if I then condition that on the data from the first flip and the second flip and the third flip, and they all come out heads, my degree of belief is going to shift from 50-50 and gradually shift towards 100% versus 0%. So after having seen an infinite number of flips coming out heads, I as Evasion would also assign a almost 100% probability for the next flip to come out heads. So again, in that limit, we tend to agree. There is, I will not, I think, go into too much details about that, but okay, what I think is important is to try to distinguish the concept of probability from the concept of randomness. At least, even though you might be a frequentist, you might think that actually deep down probabilities should be related to randomness in some sense. At least it seems plausible that we can use probabilities to talk about things that aren't necessarily random, just things that we lack information about, right? Like the outcome of the dice throw that you didn't know about. There was no randomness, it had happened, but you were still uncertain about it, so you still assigned 1/6 probability to it, which makes sense from a betting point of view. I mean, the Bayesian point of view is very much how would you bet if you were a completely rational person. But okay, a coin flip then perhaps isn't random. It's chaotic, which is effectively where I think why it looks random is the fact that it's so sensitive to initial conditions. So you can imagine that why does it come out 50-50? Well, it's effectively because in the space of initial conditions, just a very, very slight shift in the initial conditions will lead to the other outcome, right? And so if I were to sort of model my ability to sample initial conditions, my probability distribution over that space of initial conditions, if you zoom in closely enough, that probability distribution will be, because it's in a very narrow region, it's going to be effectively flat, right? So every time I sample, I sort of sample one type of initial condition or another type of initial condition with equal probability. And then through deterministic physics, they lead to a determined outcome, but it looks random because I was just sort of moving around in the space of initial conditions with effectively 50-50 probability of the type of initial condition that leads to heads or the type of initial condition that leads to tails. Okay, so that's probably not random, at least from my point of view. But what about, okay, is there somewhere, do we have random processes in nature? Is there true randomness in nature? Any quantum mechanics, right? That's the obvious choice. And the answer there is we don't know. I agree. I mean, from my point of view, I think quantum mechanics is truly random. I still believe that all the probabilities in quantum mechanics are subjective Bayesian probabilities, but I think quantum mechanics tells us, from my point of view, it tells us that nature has true randomness in it. It has true indeterminism in it. But then as sort of agents in an indeterministic world, we end up having to use probability theory because nature is unpredictable. We cannot be completely certain about what we're going to see, so we end up using probabilities. But others disagree. I mean, E.T. James, for instance, if you read his book, because he was very much from the objective Bayesian point of view, if I remember correctly, he very much doubts that the probabilities in quantum mechanics are an expression of true randomness. He is more on the approach that actually the fact that we have probabilities in quantum mechanics just tells us that we haven't fully understood quantum mechanics. So for those of you who are familiar with the various interpretations of quantum mechanics, there's a group of interpretations called hidden variables, which is essentially saying that quantum mechanics isn't a complete theory. It's very much similar to the coin toss, saying that the probabilities we see coming out of quantum physics is effectively just because we don't have complete information about what's going on. And if we had that complete information, the probabilities would go away. I disagree. I think there is true randomness. But so if one of my favorite pages on all of Wikipedia is the page on interpretations of quantum physics, because at the bottom there's a table of the most popular interpretations of quantum physics. And so you have a group of interpretations and you have a group of yes/no questions. Questions like, is physics deterministic or indeterministic? Does the observer play a role in physics or in science? Stuff like that. And you have all these like 20 different interpretations, and you see there's no pattern of effectively they don't agree on anything. Some say the world is deterministic, some say the world isn't, some say observers play a role, some say observers don't play a role. But they all agree on the mathematics. They all agree on how to compute predictions for the next experiment. So it's sort of analogous to the probability theory, right? Where we all agree on the mathematics of probability theory, but we disagree on what it actually means. And this disagreement about what probabilities mean is part of the reason why we disagree about what quantum physics means, and part of the reason why we don't agree on whether there is true randomness in nature or not. So this is another of those sort of deep connections where this question of how do we understand probability really affects essentially how do we view science, and what physics and science fundamentally tells us. All right, with that being said, I think I've been enough philosophical. Comments, questions about that?
I have one question about more dominance of the two theories, because I think most of us learn the frequentist approach in school or at university either.
Yeah.
How common would you say is the Bayesian approach?
It depends very much on your branch of science. And that's sociologically very interesting. Me coming from particle physics has traditionally been almost completely dominated by the frequentist approach. And you can sort of understand why. Because what's the sort of typical particle physics experiment? Well, it's the Large Hadron Collider or similar experiments, where you have 100 million particle collisions a second. So if there's one science where you're very much in the limit of almost infinite data, it's particle physics, right? And once you're in that limit, this whole Bayesian part, and we'll get to, I mean, part of the problem with the Bayesian, or what some people view as a problem, is that you have to assign some prior probabilities. You have to assign some degree of belief before looking at the data. And that seems subjective. And then, of course, particle physicists traditionally said, why do we want to bother with something that's subjective when clearly we can just use a gazillion amount of data. So it's only in the, I don't know, last 10, 20 years that Bayesian methods have started becoming more popular in particle physics. Go to cosmology. Cosmologists are famously happy with Bayesian statistics. And that also makes a lot of sense, because how many data points do you have in cosmology? Well, you have one universe, right? That's roughly it. I mean, of course, you have 100 billion stars, whatnot, but you sort of see that in the fields of science where you struggle with not too much data, then the Bayesian viewpoint seems more popular. So I don't know about your fields, so I don't know what fields you're coming from, but it's also then worth remembering that, except for very peculiar cases, when you have enough data, then even though the questions philosophic asked by the Bayesian and frequentist point of view still differ, they end up effectively agreeing anyway. I mean, if we have enough data, both a Bayesian particle physicist and a frequentist particle physicist will say, actually, the mass of the Higgs boson is 125.7 GeV, right? And yeah, it doesn't really matter much. That's all. Other questions? I hope I managed to confuse you. That was my main goal for today, to make you doubt most things you've ever thought about science and probability. If so, that's good. Now, I think we're gonna start by doing something boring, but I think it's important. So what I want to get to is the aspects of Bayesian statistics. I want to get there by today, but as warned before we get there, we have to sort of agree on notation. And especially important is that we need to effectively know our probability distributions. So we need to be completely clear on the difference between a joint probability, a conditional probability, and a marginal probability. So I'll just start by putting down effectively my notation, and So a quick recap on probability theory. I'll upload my notes, which are prettier than the notes are right here. Just so you'll have those available. So first of all, I will typically just use P of X to mean either an actual probability or a probability density. And I won't use sort of different notations for those because they should be clear from context. So either this means the actual probability for X, and in that case, the units of P of X is just 1. So a probability is a unitless number. So it can mean the probability for X, but it can also mean the probability density for X. And then, of course, the units are 1 over the units of X. So in that case, it actually matters what units you use, right? Because that will actually produce different numbers. So we'll be looking at a lot of probability distributions with multiple variables. And so with multiple variables, we really should do something like this. So if I wanted to use P for all my probabilities, I should make it clear that the probability distribution of some variable isn't the same mathematical form as the probability distribution for some completely unrelated variable. So then I should give them subscripts like, okay, this is my P of X probability distribution for some value of X. And I have a P of Y for some value Y. I have some P of X given Y for X given Y. Or I have some P of X comma Y for some joint probability distribution X comma Y. Or, as you often see, you'll just see people using completely different letters for all this. So they could go F of X, say G of Y, H of X, I don't know, Q of X comma Y. So we should, to be consistent, do something like this. I honestly find it more confusing than helping, except in special cases. So, but I will be sloppy and just say P of X, P of Y, P of X given Y, P of X comma Y. So I'll generally just use X for everything, and you have to read the variables to sort of understand that P of X and P of Y is not the same mathematical function. Of course, we let's just make this very clear: discrete versus continuous variables. So if I have a discrete variable, then my probabilities would just be some set of discrete numbers like that. If I have a continuous variable, then this is a probability distribution, some continuous function like that. And then some small down here, dx. So in this case, in the discrete case, then we know that the probability itself is a number between 0 and 1. And in the continuous case, we know that what's between 0 and 1 is P of X times the probability density times this small interval dx. And that is actually the probability that is bounded between 0 and 1. An important thing to remember then is that, well, for this product to be less than 1, then the probability density P of x itself can still be arbitrarily large. Right? And I can make it larger numerically by just changing my units. Right? But the actual probability is P of x times dx. And some notation that I will use and that I know is confusing because I wasted 1 week of my life due to this confusion is that we say that x, okay, we typically says that it has a probability distribution function, PDF, P of x, or say that it follows PDF P of x, or is distributed as P of x. So this is how we talk about it. The notation that's then commonly used in statistics is to say x tilde P of x. So this notation means x, the probability distribution for x is P of x. This does not mean x is approximately equal to P of x, or x is proportional to. It definitely does not mean this, and this is how I wasted 1 week of my life, because I was using this notation, and a colleague of mine was not using this notation and thought I was saying that x was proportional to P of x, or x was approximately equal to P of x, and it took us 1 week to figure out. And he thought I was being completely stupid, and I thought he was being completely stupid. But I like this notation when doing probability and statistics, so I'll keep using that. Finally, it's super important to remember that any function of a random variable or an uncertain variable is itself a random or an uncertain variable. So if I say that's the outcome of a die throw is a uncertain variable, and then I define a new random variable, which is the sum of 2 die throws, then that itself is a random variable or an uncertain variable, and I should be able to derive the probability distribution for that new uncertain variable if I assign probability distributions for the other ones. Now, let's go to the probability densities with many variables. So again, my notation will be, for instance, P of x1, x2, etc., or simply P of x vector. This is exactly the same thing. And for 2D, so if I'm just working with 2 variables, which I will use for a lot of the examples, I'll typically use x and y. But for more than 2 or 3 variables, I'll go x1, x2, x3. And then probably the most important practical matter for today is just to remind ourselves that we need to distinguish between the joint PDF, which is P of x, y, which is a 2-dimensional PDF. The conditional PDF, for instance, Px given y, or P y given x. These are 1D distributions. And the marginal PDF, which is P of x or P of y. These are also 1D distributions. So let's try to quickly make these sketches, and then I think that's it for today, because then we can start on the Bayesian stuff next time. So, of course, a joint PDF in this case is, if I'm going to try to view it from above. So x and y, this is my 2D plane, and now this joint probability distribution lives on top of this plane. And I'm just going to choose some shape for it. So say, I'll use some colors to say it's higher in this region. So this is just some color map of the shape of this distribution. And then we can get x and y. Then look at the conditional PDFs. I can, let's introduce a couple of points here. X1 and X2. Let's draw some lines there. Then we can get conditional PDFs looking, for instance, like
Doesn't work.
oh, what doesn't work?
Oh, okay. Oh, sorry.
I think it
I
works.
didn't see it.
Okay, cool. So starting from this two-dimensional PDF, right, I can get an infinite number of different conditional PDFs. And for X1 and X2, I could get two different conditional PDFs along Y, which would then look something like this, and the second would look something like this. This would be, no, that's wrong. This would be P of Y if I assume that X is equal to X1. This would be P of Y if I assume that X is equal to X2. I guess everyone, you see this, that makes sense. If not, speak up. And then, so I can get an infinite number of this type of one-dimensional PDFs. And then the marginal PDF is unique. So the marginal PDF would be P of X, would be if I start from my 2D distribution and I want to get to a 1D distribution in X, well, I integrate or sum over all possible values of Y. And similarly, if I do this, so whereas the conditional PDF expresses what's the probability of Y given some specific value of X, then for instance, this P of Y is what's the probability of Y irrespective of the value of X. And in this case, that would be if I integrate over along the X direction, I end up with something like that. This is marginal P of Y. And if I integrate along the Y direction, I end up with a PDF. Okay, didn't look like that. This is now marginal P of X. So these are unique, starting from your joint PDF, because there's only one way to integrate out a different variable, but the conditionals are, they're also one-dimensional PDFs, but you can get an infinite number of different such conditional PDFs. And I think we'll stop there, and then next time we'll actually start with the Bayesian statistics.